Hello, here's a dynamic duo again, Shackleton and Paul. And I'm continuing on my discussions on COP25 in Madrid. And I've been purchasing a few different props to bring to the conference. So here we have the present situation. $100 bills, on an umbrella of $100 bills. And then over here we have what we really need to aim for. We need to aim for a healthy planet. We need to aim for, clean environment, clean water, clean skies, air that you can breathe, no pollution. That's sort of, call it utopian if you want. But if you don't have goals, you never end up, reaching where you want to go. Okay, so I'm going to continue on with my discussions on the paper that 11,000 plus scientists, all signed up to. Shackleton is just distracting me here. Okay, so this is the World Scientists Warning of a Climate Emergency. Okay, and I discussed the first figure was the change in global human activities from 1979 to the present. Okay, and now these are the climate response time series from 1979 to the present. So here we have the carbon dioxide concentration, increasing. It's increasing at a rate of about almost 5% in the last 10 years. It used to be going up about 2 ppm, and then that's gone up to 3 ppm. Huge rates of rise, and there's no sign of this stalling out. Here we have the methane rise. So methane did stall out, but then in 2007 it started picking up again. The overall trend is up 3.65% over per decade on, and this is again 1980, 1990, 2000, 2010, 2020. Okay, nitrous oxide here, very, very powerful greenhouse gas. Global warming potential, CO2 is defined as 1, methane is 34 over 100, averaged over 100 years, 86 averaged over 2 decades, 20 years, and over 150 to 200 times averaged over a year or two, which is the key number when we have methane released in the Arctic, and it's coming up big time in the Arctic. Nitrous oxide has a global warming potential of about 300. So it's the largest, but it's in parts per billion concentrations. But it's rising 2.46% every decade, so slightly slower than methane, which is slightly slower than CO2. This is surface temperature change, plus 0.183 degrees Celsius per decade, and this is from 1980 to, hey, mister, 1980 to, you're still in the doghouse for eating my dinner a few nights ago. Details were in the previous video about that. So he's in the doghouse. He doesn't like the doghouse. Okay, so 0.183 degrees Celsius per decade rise in surface temperature. Of course, this is the global average over these decades. And about Arctic temperature amplification. The rise in the Arctic is 3 to 5 times greater. So multiply this by 3 to 5 times. The high Arctic is increasing a degree per decade, which seems like a lot, but hey, right now parts just north of Alaska, etc., are 8 degrees Celsius warmer than normal. They've been that way for months. Okay, so over here we have the minimum Arctic sea ice extent, and you can see how it increased. It is flattening out a bit. Here, it looks like the trend overall is minus 11.7% over 10 years. One thing that's not on this image is snow cover, especially in the spring. That's down about double this rate. And so snow cover in the northern regions of the Arctic is down about 23% per decade, especially in the spring. So that means the Arctic is getting a lot darker. Greenland ice mass, steep drop here. Minus 2610 gigatons over 10 years. My cat is really on the prowl. And he's annoyed because maybe he knows I'm going to Madrid, and he knows I might pick up a stray and use a stray for videos, or maybe borrow, go to an old folks home and borrow a robot cat. that I can bring in my videos and stroke, and it will start purring, and it won't be as disruptive as this guy. Hey, hey. I got my hand completely scratched. We had a big battle this morning, and you can never beat a cat. We should be honored that cats tolerate us and are our friends. Antarctic ice mass change, and of course these huge increases of melting rates. If the doubling period stays at 7 to 10 years, then and it's done that for the last 3 doubling periods. If you extrapolate that out, we're talking about huge amounts of sea level rise. It'll be something like a meter by 2050, a couple meters by 2060, and maybe 7 meters by 2070, which are ridiculous numbers. That's just what, if you do back of the envelope calculations of doubling period, that's the numbers you get. I'm not saying that will happen, but this is glaciers on land, meters of water equivalent. So the glaciers are going. We've lost 4.84 meters of water equivalent globally on glaciers on land over 10 years. Ocean heat content. The ocean is taking the vast bulk of the heat. So global warming is mostly the ocean is warming, and we're only seeing the air warming, over the land. But the ocean warming is like 97% or something of all of the warming on the planet. Then the ocean expands, contributes to sea level rise. The ocean's warmer, becomes more stratified. There's less vertical mixing, less nutrients come up from the thermocline, and therefore phytoplankton rates have dropped right off. One of the sessions that I'm a panelist in is on plankton in the ocean. If you like trees, you'll love plankton. The ability of plankton to capture vast amounts of carbon, for carbon dioxide removal methods. And we talk about planting trees. A trillion trees would put a ding in the CO2 levels, while plankton is even more important. Ocean acidity, pH. pH of the open ocean was about 8.1 or so. And 8.2, even 8.15, something like that. And it's dropping. Okay, the acidity is increasing in the ocean. If pH drops, it means you get more acidic. It's about 4.12% of acidity increase in 10 years. This makes it hard for shellfish and things to form shells. Also, half of the phytoplankton, half of them are, diatoms have a silicon dioxide or glass shell, which is won't dissolve with the higher acidity, but calcium carbonate based shells in the form of aragonite, it's called, is in things like coccolithopores and foraminiferers and other types of very common phytoplankton, and they won't be able to form their shells. That won't protect them. It'll affect their life cycle. This is a huge problem. Sea level change, of course, 31.4 millimeters increase per decade on average. That would be about 3.14 millimeters per year. And we're actually something closer to 4.2, 4.3, something like that right now. It's continuing to accelerate up. As we lose Greenland and Antarctic ice mass, all that water contributes to sea level rise. The sea ice doesn't contribute to sea level rise because it's like ice cubes floating in water. Wildfires. This is just the U.S. Millions of hectares per year. Huge increase in the area burned of wildfires. They're burning hotter. They're more intense. This is extreme weather events, a number per year, climate and water events, up 43.8% per decade, over these numbers of decades. And you can see the huge rise here. This is wreaking havoc on infrastructure and on global food supplies and everything else. This is huge economics cost. This factor alone is waking up people that we're in a climate emergency more than any other factor. And this is annual losses due to weather, climate, hydro events in billions of dollars. It's increasing at even double the rate of the number of events. So the events themselves are getting, at first order, twice as intense, twice as worse. Each event is costing more. You can see the rise here. Okay, so, have a look at the details of this paper. Just Google World Scientists Warning of a Climate Emergency and show those graphs to all of your friends and say, well, you don't think we have a problem. Okay, so I've covered the first slide, and so I'll have to go a bit faster to get through them. This is an interesting question. How much do you fear uncertainty? Because a lot of the stress and anguish that people have is because, we like to be in control of our situation and our surroundings and feel we have some control and impact on bigger issues like the climate. We go on marches and things like that. But if you look at these questions and really think about these questions, and we really don't have much control over things that happen in our lives. Most things we don't have control over. So in order to stay sane, really figure out what we have control over, what we don't, and try to change the things that you can, and things that we don't have control, like I don't have control over, what's going to happen with the planet's climate. But I can do my bit to inform people as to what is going on. I interact with a lot of the people that donate to me, and with other people. They ask me questions all the time. So this interaction, it really keeps sort of me going. It keeps me motivated and my spirits up. So look at these, and if you say not at all to these, you're probably you're probably ignoring everything. I mean, if you say this, you're like stressed to the max. Right? So neither of those extremes is good. You want to be somewhere, towards this side, not towards this side, right? Okay. This is a joke. These two people are sitting on, you probably can't read it, so I will read it. Two people are sitting on a railroad track tied together. The woman on the left says, "I can't believe we're tied together on the train tracks." The woman on the right says, "Are you sure these are train tracks?" If we work together, we can crawl off before a train comes. To the right, there's no evidence any train is coming. Okay, and then the left person, "The train comes at this time every day. Ha, what's happened in the past can't predict the future. The tracks are shaking. It's natural shaking. Haven't you heard of earthquakes? Listen to me. I'm a train engineer, and engineers are just in it for the money. Let's get off the tracks, just in case. Hurry. Expend all that effort over what might be nothing? I can see the train. We're going to die. You're being hysterical." Crash. And here they are up in heaven as angels. What's wrong with you? Okay, maybe there was a train. Okay, so I'm not talking about trains here. I'm talking about climate change. You can see, the key points from that. Okay, so I'm going to, I'll just show you some of these plots. Really good information. We go back in time. We have colder temperatures here, warmer temperatures here. These are in central Greenland from ice cores, and you can see this is a warming period. The Younger Dryas cooling. Here we are, little ice age, 8,200 year before present cooling, and and now we're spiking up, we're skyrocketing. This shows the sea level rise, relative sea level rise, and atmospheric CO2 rising over time. It's probably a bit too technical. This is a good one. Climate change, a timeline. Climate change isn't real for a certain length of time. And then you say, okay, climate change is real. We're just not convinced it's caused by humans. And this is an oops, and this is an FUCK. Very apt. CO2 mitigation curves. If we started mitigation in 2000, we'd have to reduce CO2 emissions by 4% per year. Because we're starting in 2019, we're still going up. We need a mitigation rate of about 18% a year. And these are the probabilities to have a 2/3 chance of staying below 1.5. Remaining budget, 420 gigatons of CO2. That budget will be used up in 9 years at present rates of emissions. Okay, so the only way to achieve this budget is with large negative emissions, pulling CO2 out of the atmosphere big time. Now this is an excellent plot. This is CO2 concentration. Here's where we were in 1870, 288 parts per million. All the coal we've burned since then has added 92. Oil added 70, gas added 30, cement added, land use change added, and land sinks, ocean sinks, and here we are right now in the atmosphere. I'll do a third video. Thanks for listening.